Hey guys, it's chapter 7 practice test time. Thanks for joining us. All right, question number 7.1, it says a study of voting chose 663 voters at random shortly after an election. Of these, so this must be our sample, right? Of these, 72% said they had voted in the election. The election record showed that only 53, so this number describes the population, right? Once they tallied up all the numbers. So what is true? Well, this number describes the population, which is what we call a parameter, all right? This number describes a sample, which is what we call a statistic. Okay, so when I look at my when I look at what kind of notes I should put here, let me just crop this. I don't want to just take notes on here. I want to actually turn in notes on another piece of paper that I could use to make sense of it here. So again, it's a parameter is a number that describes a population. So that could be a proportion or an actual measurement number. And a statistic is a number that describes a sample. So the answer that fits is C. 72% describes the sample, right? And 56% describes the population. Therefore, we call those the statistic and a parameter. Voila. Question number 2. A Gallup poll has decided to increase the size of the random sample of voters from about, so N was 1,500. They decided to move it up to 4,000. Right before an election. The poll is designed to estimate the proportion of voters who favor a new law banning smoking in a public building. What happens when we increase? So we've said in our notes, as N goes up, variability decreases. All right, so they took N up, so we know variability has to go down. So we look at our choices and we find it's going to reduce the variability of the expert. So since N, which is my sample size, increased, the variability will decrease. Question number 3. So yeah, this one we got C and this one we got C. All right, number 7.3. Suppose we select an SRS, N is 100, from a large population having a population proportion of P number of successes. Let the P hat be the proportion of successes in the sample. All right, so that's the symbols we've been using. For which value of P would it be safe to use the normal approximation to the sampling distribution? So we know it's safe if N times P is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. So if we set these equal to 10, we can figure out what they're asking us to kind of solve for that, which is, so we'll just kind of change this 10% condition to NP equal 10 and 1 minus P equal 10. And we know N is 100, so we'll substitute this in. So if we divide, we get, we divide both sides by 100, we get P equals 0.10. So that's why they call it the 10% condition. All right, now what about the other way around? So if we make this 100, 1 minus p equals 10. If we distribute the 100, so we get 100 minus 100p, and we add 100p to both sides. And we subtract 10. We get 90. And we divide by 100. And this makes sense. The 10% condition means I need at least 10% to say yes and 90% to say no. So that would be 90%. So they ask which of these p's would meet normalness. So I need p to be any number between 10% and 90%, right? To make sure that my 10% condition is met. So when I look at my choices, nope, 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 this is the only sample that fits. Got me? So my answer is 0.85 would meet my 10% condition. All right, question number 4. I just need another piece of paper here. Question number 4 states, the central limit theorem is important in stats because it allows us to use normal calculations to find probabilities involving the sample mean if. So we're finding which one is describing the central limit theorem. The central limit theorem states I have to have n greater than or equal to 30, so I don't do the 10% condition. That's for a proportion question. Central limit is for a mean question. We need a sample sufficiently large as long as if n is greater than or equal to 30, then the sampling distribution will be approximately normal regardless of whether the population distribution is skewed. Okay, so which choice matches with that? That matches with A. My sample size is sufficiently large for any population of any size. So I get A. So what's wrong with the other ones? Well, the population is normally, the central limits theorem states that the population is normally distributed. Well, no, we have plenty of population distributions that are not normal. It works because the population is normally distributed. No, population distributions are not always normal. The population is normal. No, the population is not always normal. The population size is reasonably large. No, we test out the sample size, N. The sample size has to be sufficiently large. And we deem sufficiently large to be right around 30. All right. Question number 5. Okay, so I'm going to actually just duplicate this sheet. Duplicate. Beautiful. And I'm going to do the other side. All right, so question number 5 says, a number of undergraduates at Johns Hopkins is 2,000, right? That's the population at Johns Hopkins. And the number at Ohio State, so the number of the population at Ohio State University is 60,000. At both schools, a simple random sample of about 3% of the underclass was taken. So 3% of 2,000 is, and 3% of 60,000 . So that'd be 60 people. And this would be 600 times 3. All right. So if we took a sample, so that would be n. And so when we find n, the number of our population, oftentimes they use this capital N to mean the population size. And little n is my sample size. Okay. Each sample is used to estimate the proportion of all students at the university who owns an iPod. Suppose that in fact P is 0.8 at both schools. Which of the following is the best conclusion? So when we're asking a question of proportion, right, then we know we have to have the 10% condition met. So we could do n times P. They said the proportion is 80%. So 60 times 80%, and then n times 1 minus P. So 60 times 20%. And so I think this would be 12, and this would be, I'm trying to do this in 68. So that's fine, even though this is a small number. Now this one's definitely going to be fine. I'm not even going to do the 10% condition. So we're not saying that we're not asking enough people, but we would expect that the estimate from Ohio State would be closer to the truth than the estimate from Johns Hopkins because it's a larger sample. All right, so what does that mean, closer to the truth? Well, again, we know that as n increases, so we get D, then variability decreases, meaning when I say variability decreases, that means that it's skinnier. This is my prediction, and this is how far off from my prediction I have. So that's what that means. I'm going to be closer to the truth because this is such a large sample. All right. Question number 6. So T7.6. A researcher initially plans to take an SRS size of 160 from a certain population and calculate a sample mean. So this is a means question, not a proportion. Later, the researcher decides to increase the sample size so that the standard, so this one's the old one, and then they make a new one where this is bigger. Maybe 10 times bigger, I don't know. Later, the researcher increases the sample size so that the standard deviation of the sampling distribution will be half as big. So as n goes up, the variability goes down. What is the sample size the researcher uses? So we know that the sample size, if the standard deviation went down, n has to get bigger. So it can't be that. It can't be that. So it's got to be this one or this one. And we can figure that out. So my standard deviation of my sample is my standard deviation divided by the square root of n. So if I say my old one, it's now half as big as it was. So if this was my old one, then these two would be equal to the new one. But this one is half as big. So you would have to take 2 times this one, right, for them to be equal. So again, if this ended up being, I don't know, standard deviation of 8, then this would have to be half as big, so that'd be 4. So you see how I set up that formula? 4 is half as big as 8. I could have also shown it as this is half over here of the old one is equal to the new one, okay? So looking at our formula, we say, we don't know what sigma is, but we know the old one, okay? So the square root of the old one is equal to 2 times the square root of the new one, which is either, we don't know, it's either 320 or 640. So notice we can do some Lynch swapping here. I can move this square root of n up here, and I can move the square root of 160 up here, and I have 2 sigma, and I have sigma. All right, so I moved everything to the numerator, or you could think of it as cross multiply and solve. And see how I can divide sigma on both sides. So it doesn't matter what sigma is. I can square both sides. Right, so you get n is equal to 4 times 160. Okay, so that would be 0, 4, 2, 640. That's our answer. All right, 70, that was 76, so 77. The student newspaper at a large university asks a simple random sample of 250. Do you favor eliminating a carnival from the end of term celebration? All in all, they took a sample and 150 are in favor out of 250. Suppose that unknown to you, 55% of all undergrads favor the elimination. So they're saying sometime later they asked and they did end up finding out this was the proportion. So let's see what our sample proportion is. So it's 150 over 250. So looking at our calculator, have I completely lost my calculator? $150, are you kidding me right now? Divide by 250.6. So your sample was close, and later on they found out, or maybe they just, asked everybody, and it's that, right? If you took a very large number of SRSs of size 250 for this population, the sampling distribution of the sample portion would be what? So we know that the sample is centered around P, and the standard deviation would be sigma of our sample would be, I'm doing a proportion question. So that's P, 1 minus P over N, take the square root of the whole thing, right? That's the square root of my sample, the standard deviation of my sample. All right. So we look here and it says it will be approximately normal. That would be true as long as this 10% condition is met. So N times P, and I'm going to use this number, right? 0.55 has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10, so 250 times 0.45. So they're big, times 0.55. Yep, 137.5. 50 times 0.45. 112.5. And of course, yeah. So we can say they're approximately normal because of the 10% condition. And where would it be centered? It would be centered at this truth, not on my single sample. That's a single dot. It'd be on my proportion. So I'm looking for the answer at B, a mean of 0.55 and a standard deviation of 0.3. So where did that 0.3 come from? 0.03 comes from 0.55 times 0.45 divide by 250, take the square root. That's where that number comes from. Awesome. Check out the next video for the next page.